Here we go, moving into section 5.4, which is just titled Working with Integrals. And a lot that we have to do in this section is basically trying to make things a little bit more efficient with us using the fundamental theorem of calculus. So, with the fundamental theorem of calculus in hand, we may begin an investigation of integration and its applications. In this section, the role of symmetry in integrals will be discussed. The slice and sum strategy will be used to find the average value of a function, and a theoretical result called the mean value theorem for integrals will be explored. So let's get into this. In anything that you've done kind of some math analysis, college algebra course, algebra 2 course, you might have talked about even and odd functions. And a lot of times the extent of that is a function even, is it odd, is it symmetrical with respect to the x-axis, the y-axis, the origin, etc. And so we're going to use that idea of symmetry to be able to help us out with some more efficient integrals. So why is symmetry, or when symmetry is used, this leads to insights and efficiency. So symmetry will be used here to make integration simpler. Let's remind ourselves of even and odd functions. So we are going to look at the definition of an even function. And if you recall, in each time what we have to do is throw in negative x into our original function, and the result will be different whether it's an even function or whether it's an odd function. So if I kick back the exact same original function after plugging negative x into that function, then I end up having an even function. Now, some examples of an even function would be like y equals x to the n, where n is even. Hence, if I look at a trig function, cosine is actually a trig function that is even. And what you will find with both of these, thinking about like y equaling x squared, that's the lowest even that we have, and that's the graph of y equaling x squared, then this is symmetric over the y-axis. And so when we talk about areas under a curve, if I look at kind of the area from here to here symmetric over that y-axis, the area here should equal the area of that. So basically what I can do, what we're going to find out, is that we can just double this area and find the area of the whole thing. So we are going to then look at odd functions as well. And if I throw in negative x, that means I kick back the opposite of the original function. Now, some examples of this could be x to the n power, where n is odd. So it could be like x cubed, y equaling x to the 7th. They each take on kind of this type of function when you are looking at an odd thing of 3 or higher, odd power 3 or higher. It is going to be symmetric over the origin. So that means that like if I have the point 1, 1, then the opposite of each one of those points, -1, -1, is also a point on there. For a trig function, sine is our most basic trig function that we have, or a common trig function that is actually odd as well. Okay? Alright, so special things happen when an even and odd function are integrated over integrals centered at the origin. So let's investigate. So I actually may have given away what we were doing here with our odds. So let's just go and formally write, if I have y equaling x squared, what does that look like? Well, I have a parabola that is pointed upwards. It is an even function, therefore it is symmetric over the y-axis. And say I wanted to go from -4 to +4. Okay, so we are centered at the origin of our interval here from -4 to 4. And if I look at the area here and the area here, then when we bound it using integration with the x-axis, those are the areas that we are looking for. Now, what we could say and observe is that we have equal areas to left and right of the y-axis. And if I look at sine, y equaling, or not sine, excuse me, cosine, that's an even function, then the graph of cosine goes up to 1 and down to -1, and so we end up doing something like this. And I'm going to look at negative pi over 2 to pi over 2. So again, we're centered at the origin, and we're concerned about the area under this curve from negative pi over 2 to pi over 2. And notice here that we have two areas that are in question. And if I were to do this actually with a tool, or actually more precise than just by my freehand, then you should recognize that the area on either side of these have the same amount. So again, we have equal areas here, and so what we can do and think about is that we can double one area. So can double one area, and the area I always like to use is this on the positive side, because you have 0 as an integrand and a positive x value over here. It's not going to matter which one that you do, you'll have 0 either way that you go, but no need to go from negative pi over 2 to pi over 2 when you can go from 0 to pi over 2 and just double it. So we will see that here shortly. Now, what if I look at the most basic odd function here? Well, I guess we could do y equaling x, but let's get something better than a line. Here's my y equaling x cubed, and say that I'm going from, say, negative, or that's a positive 2 to negative 2, and I want to look at the graph that is bounded with the x-axis and the function. So I have this piece, and again, I'm not very accurate with my freehand drawing here, but if I were, then the area here is the same as the area here. But the difference is that on the even function, both of those areas are above the x-axis, so that's how we can double that. Here, one of the areas is above and the other is below. So when we talked about integrating and it being the net area, I had to account for this region to be negative. So if this is like negative 10, this would be positive 10. Therefore, the integral from here to here, these things cancel themselves out. So we have equal areas, but one is positive and one is negative. Therefore, the net area equals 0. So let's see if I can convince you that on a trig function as well. So let's just take sine, and sine of x around the origin. Normally the sine function will kind of go up and it will go down and like this, but then it'll end up coming like this on the other side of the origin. So I'm going to say maybe I'm looking at negative pi over 2 to pi over 2. Now you could actually do from negative pi to pi, but as long as it's centered at the origin, these things are going to occur for any odd function. So notice here, this one looks a little bit better, that this area equals this area over here. One is positive, one is negative. Therefore, your net area is going to equal 0. So, whoops, let me scroll down here. Keep scrolling a little bit here, and here gives us kind of our culmination here of what we just discovered. We're going to let a be a positive real number and let f be an integrable function on the integral from negative a to a. A lot of times that's a to b. But here, remember, we are centered over the origin. If you want to put that there as a reminder. All right, so if f is an even function, then the integral from negative a to a of f of x dx. Now remember, this is the even function where I have the same exact areas, both of them being positive or both of them being negative. Therefore, I can double the interval from 0 to a of f of x dx. So again, the advantage of having 0, a lot of times if these are polynomials, being able to evaluate using your fundamental theorem of calculus is a little bit easier. Now, if f is odd, this is so nice, that if I have the integral from negative a to a, which represents the net area from negative a to a of f of x dx, that is equal to 0. So being able to remind yourself how you find an even function, how you find an odd function, and be able to identify those functions is important to save yourself just a little bit of time. Okay, so we have two integrals here. Both of them have a difference between each of the terms. And so remember, with integrals, we can separate each one of those terms separately. So I'm going to do just that. So I'm going to say that from negative 2 to 2 of x to the 4th dx minus integrate from negative 2 to 2 of 3x cubed dx. Now, I want to decipher whether or not I have an odd function or an even function. Now, if you have polynomials, x to a power, remember what we said on the back side, in order for it to be even, then the n had to be even. So if you have any power term, then you just have to know, does the power, is it odd or is it even? Therefore, what we can see on this first term here, this is an even function. And this whole thing is an odd function. Now, if we do that where we are symmetric over the origin, or centered over the origin as what I had said, then we know for an odd function from our property we just saw in the box before this whole thing becomes 0. So we don't have to integrate it. Now, for an even function from two values that are centered over the origin, that means that I can now change this from 0 to 2, but I'm going to double whatever area that I get from 0 to 2 to get the total area between -2 and 2. So I need to integrate twice from 0 to 2 of x to the 4th dx, and that's going to give me my answer. Now, when I do that, that means that I have to use my power rule. Don't drop your 2 out front. I'm going to add 1 to the power and divide by that new rule, or the new power, excuse me, and evaluate from 0 to 2. Now, you can, if you want, pull out the 5 and just do 2/5 times that amount, which might be a little bit easier. But you have 0 here to kind of cancel things out as well. So I have twice of, when I throw 2 in, 2 to the 5th is 32/5. And then when I throw in 0, well, that's still just 0. So technically I get twice of 32/5, which multiply the two tops together gives me 64/5. And that would be the net area for this function from -2 to 2, or that is the integral there for that function. All right, so we're centered at the origin because we're going -pi/2 to pi/2. We have two different functions here. So again, I'm going to separate in a sense, and you don't always have to separate, but I like to do this just so that you see it separately. I'm going to also choose to bring the 4 out front, okay? And so I get sine cubed of x dx, and I'm integrating from -pi/2 to pi/2. All right, now, which of these are even, which of these are odd? That would be the question that we'd have to ask ourselves to save ourselves a little bit of time. So if you don't remember, or if you're not comfortable with trig as much, make sure that you remember which ones are even or odd, or make sure you investigate with a few powers. On the reverse side, on the examples I told you, that I said that this was actually an odd function and our cosine is actually an even function. You can also look at the graphs to see if they're symmetric over the origin and the y-axis. That would tell you as well. So if I'm integrating an odd function from points that are centered around the origin, those areas cancel themselves out and give me 0. So basically all I'm left with is integrating this, whoops, I forgot my dx on this one, integrating this function and evaluating from -pi/2 to pi/2. But since this is an even function, then my property tells me that I can integrate from 0 to pi/2 of that function and get the same answer. Okay, so I want twice of, what do I have to take the derivative of in order to get cosine as the derivative? Well, that should be a sine. Hopefully you're yelling that at me through the computer, and I want to evaluate at pi/2 and 0. So remember, by the fundamental theorem of calculus, I must evaluate this one first, then subtract the difference of that one. So what I get is twice of the sine of pi/2 minus the sine of 0. Make sure you find each one of those values. Now here, this, again, make sure you know the graph, or make sure you know your special angles of your trig functions. This is 1, sine of 0 is 0, therefore when I multiply by 2, I get an answer of 2. So those are working with even and odd functions to make life just a little bit easier. Now, will you notice that every time? Probably not. You just kind of, in the rote process of doing it, may miss that. But if you do see it, it does make life just a little bit more efficient. All right, now our next idea of average value leads into our last idea of what we call the mean value theorem. We had a mean value theorem for derivatives, but now we have this for integrals. Now, our average value of a function. If 5 people weigh 155, 143, 180, 105, and 123, their average weight is found by adding all the weights and dividing by the number of people to get 141.2. So add them all up, divide by 5, that's your mean or your average. This idea generalizes quite naturally to functions. So, with a very minimal proof, the average value for functions can be derived, and I believe it is also in your book if you'd like to go see that. The average value of a function is analogous to the definition of the average of a finite set of numbers. So, basically you have a function, if you want the average value of that, you are going to find the values of that function, add them up, and divide by how many that you have. And so, it's pretty slick on the proof with that, but here is the definition of the average value for a function. So, the average value of an integral function f on the interval from a, b is defined to be, and they use kind of f with the, this is a mean, when you find an average in statistics, you put the little bar over it, so they use f with a bar to represent the average value. It is found by taking 1 over b minus a, that's like dividing by how many that you have, and integrating from a to b of your function dx. Okay? So a big part of this is making sure that you know what the formula is so that we have it, okay? Now, the average value of a function on interval AB has a clear geometric interpretation. So I want to kind of give you what the meaning of that means and what it looks like. And the way that we do this is by multiplying both sides of the definition by b minus a. So I'm going to multiply by b minus a, which would cancel that, bring that over here, and I get b minus a times f bar is equal to a to b of f of x dx. Now, from our previous topics, we know that with this definite integral that we have the net area under the curve that we are finding when we're looking for the integral from a to b of f of x dx. Now, what I have here is the net area of a rectangle. Now, what rectangle am I talking about here? Well, let's draw us a little picture, okay? So I have some function on the interval, say, from a to b, okay? Now, if I'm finding the area of that curve, underneath the curve with the x-axis, that red part is the integral from a to b of f of x dx is in red, okay? Or this way in the direction. Now I'm going to change colors. So if you have a way to change colors and want to do so, please do so. Now, the other is the net area of a rectangle. Well, b minus a is this distance. So that means if I'm finding b minus a, that would be my length of my rectangle. The mean, the average value, would have to be my width of my rectangle. And remember, f bar is just a number. So it is a value here along our y-axis. And if I create a rectangle, then this is the area of that rectangle. So b minus a of f bar is in blue. And I did the lines going in that direction. So, what we're saying here, the geometric interpretation of this mean basically says if I take the area under the curve, I can find an equivalent area of a rectangle on the same graph in which those two areas are equal. This f bar here is what makes that happen. Okay, so if I were to draw a smaller rectangle, the area of that rectangle is not going to be equivalent to everything in the red. So we have to find that happy medium of where they are exactly going to be equal, and that's what we refer to as the average value. Okay? Which is important for what we are going to learn here soon with the mean value theorem. Okay, so let's do an example of this, and this is an application of average value. A hiking trail has an elevation given by this nice long polynomial function where f is measured in feet above the sea level and x represents the horizontal distance along the trail in miles. So we're going from 0 to 5 miles on this trail. what is the average elevation of the trail? So here's the elevation, which is my function. If I want to find the average of that function, I'm going to be finding the average value of that function, okay? So first, I'm going to look at what is 1 over b minus a so that I can put that in front of my integral. Well, from this integral, this is a, this is b, therefore 1 over b minus a is 1 over 5 minus 0, which is 1/5. Some really bad writing, I apologize. Okay, 5 minus 0, 1/5 is that 1 over b minus a. So if I want to find that average value, that means I need to do 1 over b minus a times the integral from 0 to 5 of this polynomial. Now don't panic, those are big numbers, but they're not going to let us get to us. They're not going to scare us when taking this antiderivative. So now I have a definite integral that I need to integrate, then evaluate at 5 and 0 and multiply by 1/5. That's how I find the average value. So let's go ahead and integrate our polynomial. So let's try to do this in our head. If I add a power to 3, then I get an x to the 4th that I would have to divide 60 by 4. Well, 60 divided by 4 is 15. Therefore, I get 15x to the 4th. Minus, add a power to the x squared gives me x cubed. Unfortunately, when I divide by 60, it does not go, or divide by 3, it does not go in evenly to 650. Plus, add a power here to my 1. That gives me an x squared. When I divide by the new power of 2, that gives me 600 x squared. And then this is a constant, therefore it should have been a linear term in my original function in order to take the derivative to get 4,500. So that is what I want to evaluate at 5 and at 0. Now the 0 is going to be very, very nice, because the 0 here, 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 and here is going to be gone. So I really only have to evaluate it with the 5. So I'm going to do 1/5 of throwing 5 in, taking it to the 4th power, and timesing it by 15 gives me 9375. Minus, again, throwing 5 into the 3rd power times 650 over 3 is 81250 over 3. Squaring 5 gives me 25. Multiplying by 600 is 15,000. And multiplying 5 by 4,500 gives me 22,500, and that is the evaluation for a or x equaling 5. But I'm going to subtract here the 0. I'm just going to put a 0 there so you don't forget to evaluate at f of a as well. All right, so when I add and subtract these together, I will tell you, and have your scientific or graphing help you do that. I'm not evaluating if you can put fractions together or not. Get a tool to help you do that if you need to. And then, whenever I add or subtract all those up, this is 5937 over 3. I know that 5 will go into this value here, and it is 11,875 over 3. That right there is the average value in feet of that distance, okay, of the elevation. All right, very good. So that was an example that leads us to our mean value theorem for integrals. And the mean value theorem of integrals holds very closely true to this average value of function that brings us to this theoretical result. Let's revisit the graph that we constructed for average value. So I'm going to even do it in the same colors. So here was my graph. I ended up having some function from A to B, and this was the area of that function. The average value brought in this rectangle where I ended up having some f bar that whenever I created the rectangle on the same interval, then the area of that rectangle equaled the area under the curve. Now, the mean value theorem is nice because it goes one step further. It doesn't just give us the average value that it's equal to. There is a certain value C here at which that occurs, okay? At which those two values are equal. And right here, maybe I should do it in a completely different color. This value right here, when x equals C, is the value at which those two things are equal. The area under the curve is going to equal to the area of that rectangle created by the interval and that average value. So these should look very similar. The mean value theorem for integrals said that there exists a value such that the function value of this is equal to the average value of the function. So let f be a continuous function on the interval from a to b. There exists a point C on AB. Now, I'm pointing out here, this is an open interval. C cannot be on the intervals. Such that f of C is equal to the average value, which is 1 over b minus a times the integral from a to b of f of x dx. Okay? AKA over here, you may want to think where we have f of c equals the average value. So the difference here is you're not just finding the average value, you're solving the equation to find the x value that makes that true. So let's do that by example. Find the points at which our f of x equals its average value on 0 to 1. First thing I like to do is to distribute that 2x because I don't like to see the product there when I'm going to have to integrate. And so what I normally do is I find this part first, okay? That I want to know that this, and I'm going to do this so that you remember the notation for the average value. Here the average value is 1 over b minus a, so 1 minus 0, well that's awfully nice. And I want to integrate from 0 to 1 of the function that I just modified so that I can integrate it more easily. So, f bar, this is just 1. I'm not going to rewrite it. But I'm going to integrate this guy right here. Add 1 gives me x squared. When I divide by 2, that goes to a 1, so I'm not going to write it. Minus, then I'm going to add 1 gives me x cubed. Divide by 3 gives me a 2/3. And I want to evaluate that at 0 and at 1. So, by the fundamental theorem of calculus, I can throw 1 in, square it and get 1. Throw 1 in here, cube it as 1 times 2/3 is 2/3. Subtract, throw 0 in here is 0, and 0 in there is also 0. So there's the full fundamental theorem of calculus, and it all goes down to, that's gone, taking 1 minus 2/3. So 3/3 minus 2/3 is 1/3. So that's the average value that I want to find and set equal to this guy right here so that I can figure out the x value. Now, it does say f of c, so if you want to plug c in, which gives you 2c minus 2c squared, the x's in c doesn't really matter. I normally will put it in terms of x. So here, we want to know f of c equals 1/3, or where is f of x equal to 1/3? And then when you solve for x, x is going to be your c value. So I'm going to set 2x minus 2x squared equal to 1/3, and I have to solve this. Well, it is a quadratic equation. So I don't like that 1/3. So I'm going to think about multiplying everybody by 3 to begin with. Okay, so I get 6x minus 6x squared equals a 1, because those 3's cancel. Now I don't have to worry about a fraction. Okay, but it is a quadratic that I have to get equal to 0, and I like having this term being positive, so I'm going to think about adding over 6x squared and subtracting the 6x. So I get 6x squared minus 6x plus 1 equal to 0. Now, I will tell you the easiest way to solve this is to factor. But unfortunately, sometimes things won't factor. So this, I will tell you, can't be factored. As many times as you try, it's not going to factor. So we have to use the quadratic formula or completing the square. If I were you, I would use quadratic formula. That's what I'm going to do. So that is that big long formula, x equals the negative of b plus or minus the square root of b squared minus 4 times a times c. So I get 4 times a times c all over 2a. So don't forget the 2a in the bottom. So at this point, I just have to kind of simplify. So I get 6 plus or minus the square root, 36 minus 4 times 6 times 1, that's 24. So 36 minus 24 is 12 all over 12. Okay? Now, here, remember, C has to be in my interval. So C has to be between 0 and 1 in the open interval. So I want to check these values to see whether or not I end up having both values be within A, B, or just one. So you can plug these into your calculator. Go 6 plus root 12 over 12. That will give me 0.789. And then if you do 6 minus root 12 over 12, you're left with 0.211. Notice the decimal values of those are both within the interval. Therefore, you do have two C values at which that rectangle value is equal to the average value. So if it's an estimation or an approximation that they want for the C values, you would use your decimals. If they want the exact in the online system, you would definitely use the quadratic exact form for that, okay? Now, if you needed to simplify this, remember this is 4 times 3, so they may go as far as saying, okay, well that's 2 root 3 all over 12, and I can cancel a 2 with all of those. So it may be that they ask you for this final answer for an exact value. So be very careful when they ask you and watch the directions that they ask you for that. But basically, like I said, we're solving for when the function is equal to your average value. So, finding the points at which f of x equaling x, absolute value of x plus 2 equals its average value. So find the C that makes that occur. Now, if we were to graph absolute value of x plus 2, that plus 2 gives me a shift up by 2. And if you recall, absolute value is a V. Okay? Now, we're looking at -2 to +2. Again, I'm not very symmetric, okay? And so, don't forget, this is actually, we're going to use the first part of this section. This is symmetric over the y-axis, and it's centered at the origin. So therefore, I can use the symmetry where we can double the area from 0 to 2. So let's do that. So when finding the average value, then I have to do 1 over b minus a. So there's a and there's b. So let's go 2 minus a -2 times the integral from, I'm just going to write it out here at first, -2 to 2 of the absolute value of x plus 2 dx. Now let's talk real quick here. Let's simplify. This gives me 1 over 4. Now again, I'm going to double from 0 to 2, but let's stop right here at f of x. Unfortunately, we don't know how to integrate an absolute value of x. What you have to recall is that the absolute value of x is actually a piecewise function where you have one of these functions here and you have another function here pieced together. Now it's all going to derive off of having a positive version of this or a negative version of that. So if you were to write the equation just from 0 to 2, and it's a line, think of that line coming all the way down here. It's plus 2 and you have a slope of 1. So this is the function y equals x plus 2. Now why? Because any value that you have here that you plug in here and take the absolute value, it's the exact same value. So you would kick out just an x. But if I were to take any of these values, say a -5 in, the absolute value of that is the opposite of that. So that is why this line, taking the opposite of what's inside that absolute value, is -x plus 2. So it's really tricky on those absolute values. You want to make sure that you can split them up. So we're going to integrate from 0 to 2. So the only function I have to care about is the x plus 2. So that's what I'm going to integrate here in terms of x. Okay? So I kind of split it up just so you see step for step. So this is f bar and this is f bar. What we're going to equal to, I'm going to take 1/4 of 2. So I'm going to combine these two together to get a 1/2. And I'm going to integrate this x plus 2. So I'm going to add 1, gives me x squared, and divide by that new power is a 2. And then plus 2x that I have to evaluate at 0 and 2. Again, 0 is very nice. Those are going to go away whenever I evaluated that. So 1/2 of, throw 2 in there, 2 squared is 4, 4 divided by 2 is 2, plus 2 times 2 gives me a 4 minus, here's the time we throw in 0. So I get 0 plus 0. Sometimes I just like to do that to make sure you see where that's at. That goes away. This gives me a 6. So I basically get 1/2 of 6, which is equal to 3. Now remember, that's the average value. And my task to find which points, they're asking basically, aka satisfy the mean value theorem, at which points is that equal to the average value. So now I need to take this equal to the function. So now I need, when is f of x equal to 3? That's the question. So when is the absolute value of x plus 2 equal to 3? And this is an absolute value equation that we haven't had to solve too many of these, but it's pretty easy. Isolate that absolute value by itself by subtracting 2 from both sides. So you get the absolute value of x equals 1. And when you get the absolute value by itself, then basically you take what's inside there and set it equal to plus or minus the value on the right side. Because if this is a positive 1, the absolute value of a positive 1 is 1. The absolute value of negative 1 is also going to be 1. So therefore, these are my two answers that are possible. And maybe I should not have circled it so quickly because are they in this interval? You have to check to make sure that they are in that interval. Negative 1 and positive 1 are both in the open interval there. So yes, there are two C values, just like there were in our previous example up top. Okay? All right, very good. So that would be the end of section 5.4. And we are going to be able to move into section 5.5, which actually kind of helps us with some more techniques on how to find some integrals like we did at the very beginning of this section. But definitely make sure in section 5.4 that you figure out the average value and the mean value theorem, because those are important to make sure that you can master. So until next time.